Hi. Hi, I'm Filip. I'm a network programmer at Sirocco Mobile, currently working on a massive multiplayer server for a mobile sport game. I'm glad that you're here at this last technical speech today. It's not so popular theme. But you're sitting here, so probably you mean that a part of you are interested in creating multiplayer games. So maybe a part of you are already unhappy with your previous experience with frameworks like UNet or Photon or something similar, or you're just curious. Anyway, I've tried to make this speech more about approach instead of concrete implementation, but to be honest, I failed at that because there will be many code examples in C# because I'm .NET and Unity developer. But if you are a C++ programmer, stay tuned because underlying technology remains the same, and network layer is not related to game engine at all. It's just the same language. And please, if someone is interested in some part of code from slides, don't focus too much on that. I can send this presentation to you. Just ask me for that. I will not talk about UNet. To be polite, because we have guests from Unity, because I don't like it. It's not supported technology anymore, anyway. And I will not talk about Photon either, because even if it's better, it's similar in architecture to UNet. So it's nothing that I would like to recommend to you unless you want to create casual games. But to be serious about Photon, today we're gonna talk about massive multiplayer, and I don't want to say that Photon cannot handle your network traffic, because it's not true. It's more about your network interface device. But in my opinion, if you think seriously about creating multiplayer games, you have to invest your time and build your own network anyway. And it seems to be pointless if we try to build a scalable, data-driven, designed backend at the top of the object-oriented framework that implies architecture style to our gameplay, because this frameworks works like a parasite attached to our game objects. It doesn't scale, and it binds very hardly our gameplay layer with the network layer. And what I suggest is some layer separation, because many developers doesn't understand it well, but multiplayer game is not a network-driven application. Multiplayer game is a data-driven application, and what it means for us that this network layer should be separated from the gameplay layer. And if it is reusable in a huge part. We can easily and fast prepare it for any other kind of activity, like the other games, business application, chat system, whatever. In the name of single responsibility is just a layer that provides us efficient, reliable and unreliable communication between endpoints. That's all. And such a layer is also scalable. We can scale it down by merging the threads that it uses, or scale it up by vectorize it through many threads. And vectorizing is a key for efficient multi-threading, but to make it possible, we have to code it in a particular way. By vectorizing, I mean when we have, for example, clients, and we split them into the buckets, and we run a separated thread for each bucket. So I created this lecture at the top of the common problem, maybe not so common, but especially for young programmers. So let's assume for a while that we are interested in creating MMORPG, of course, kind of isometric MMORPG. Network layer is a very small piece of that cake, but it's a great example for scalable networking. I had a few assumptions. The first one was a single server architecture to make it closer to the indie studios. And what I mean by that, I'm not talking about databases or web services, because of course it should be always separated from the server. But I mean that the whole game world should be simulated by a single machine. So we don't have to handle data between many physical machines inside one world. So we don't have to be connected to the database all the time. We can just push a kind of snapshot back up to the database sometimes. I wanted to handle up to 1,000 simultaneously connected clients and up to 21,000 simultaneously active dynamic network entities. What I mean by that is if we have 1,000 clients connected to our game, and each of them choose a different position on the map and aggregate up to 20 unique entities. along the world, then we end up with 20,000 of them. So that's the number. It scales simultaneously with our gameplay. And we are talking about 3D game. So we are talking about simulating AI, pathfinding, crycasting, everything. So this number is reasonable. And at the end, it should be hostable on a regular machine. So it's just like Ultima Online. It was done already. And if we're creating a single-player game, it's a standalone application, mostly input-driven, that obviously have simulate everything on our local machine. But if we're creating a multiplayer game, client in such game is responsible just for displaying a gameplay and forwarding the client's intentions to the server. So it's just like TV with remote control. It's nothing special. So if we're creating a strategy game, for example, and we have to simulate a world for hundreds of entities, then probably we start to care about performance, and we start to optimize our game. So if it's a multiplayer game, we have to multiply our optimization by server capacity, because at the end it's look like this. There is something around 1,000 clients here, and a regular home-based PC in the middle that have to simulate a world for tens of thousands of entities. Of course, without animation, that stuff, but still. And comparing it to the same single-player game, this network architecture that we're talking about today is just an additional part that we have to add to our game to make it happen. And obviously, such game require a deeply understanding of what we are doing, how our network, not only network, but our data flow in an application. So if it's a multiplayer game, we should understand as well a network layer of our game. We should understand what will generate most of network traffic. Even before we start to code the game, we should understand what structures we're gonna use, how big they are after serialization, how this serialization takes, when we have to send them to whom, how frequently. And obviously, third-party solution looks more like this. It can, we often can't even see what's happening inside. We can optimize it, which is bad because each game is different and require different approach. And is the main reason why networking that is created for any type of game can't be applied into more demanding ones. So to make this server domain more clear, let's start an example. It's our isometric MMORPG client, and this client intention is to move its character to the right. And for purpose, I'm not talking about player inputs, because from the server point of view, we are not interested in how this player retrieve this vector direction, or how he wants to pay for network latency or perform client-side prediction, because it's more about design. The technical issue here is that this intention should be serialized in the form of data model, and it should be pushed to the server. And the server is the real one who perceives this movement. And server have to perform any kind of action for all the players, all the server network entities, and at the end, server have to grab all of this data and push it back to something that I like to call the circle of interest, which we'll talk about later. Even if we perform our client movement locally on the client side, even though we have to interpolate these positions, if these positions are more diffuse than threshold that we have set, later on when these positions come back to us from the server side. Because if we try to make this movement happen on the client side, and we push our position to the server, we always end with something like this, like with network transform from UNet, for example. Because server knew better where our entity is, how fast he is, what obstacles around, what should be serialized to such entity. So when we are creating multiplayer game, we always have to think about this, that the server is the king, and there is no real gameplay that's happening on the client side. And going forward, of course, everything goes through performance when we want to scale. So object-oriented programming is great. It's juicy in code, especially in C#, but it's not so friendly for our CPU. So we have to use data-driven design, data-oriented programming. However you name it, you have to use it because it's much easier to maintain. We have simple structure with clear entry points. And because at the end, if we have this 1,000 clients connected, and if we assume that each of them are connected on the IPv4 and send us only empty UDP packages, datagrams, such datagram is not, it's minimum 28 bytes. And even if we assume that we do not receive more than 30 requests per second per client, we have to be capable to handle, receive, deserialize, and handle 30,000 of such requests. So if these requests are empty, we are talking about 0.8 megabit per second. So it will be probably, in average, something between 1.5 to 2 megabytes per second. And servers still have much more to send than received. Each request in this architecture should be received, deserialized twice, and handled. And serialization, it's not your bottleneck. You shouldn't bother too much about this topic. I suggest to use protobuf because it's great. It's a C++ Google technology, but you can grab a protobufnet from the Nugget in C#. If you are a Unity mobile developer, then probably use Stack with Newton soft.json, the one from the asset store, which is slower and requests are bigger, but it's still enough. It's still not your bottleneck. You shouldn't treat requests individually. Instead of that, you accumulate them on outgoing request queues on both client and server side, because it's more appropriate if we have a separated thread that sends this request. The one point in application that touching our sockets with the clients. So when I'm sending this requests from the queues, I always serialize them as network requests RI, even if there is only one request to send from a particular queue. And even if we realize what will generate most of our network traffic, like in such a game, like this isometric MMORPG, probably over 95% of our network traffic, incoming network traffic, will be filled up with something like this, as serialized direction of some kind of intention of the movement, and some additional state probably. Even though we have to realize what can generate uncommon network traffic part in our game, because it can corrupt our main synchronization loop. In such game, like in this stolen Ultima 6 example, it can be a place which in player may enter the city market. And if we have randomized items in our game, we can think about it earlier, because we can avoid a situation which we have to send him a phone book that describes all of these items attached to all the players and around all the NPCs. So we can recreate these items locally on the client side based on a very small piece of information and known seed. Because going forward, player may enter the city very often, and result we can often send him unchanged data that describes the same entities that he just saw. So probably it's probably the only place which I can imagine that player may ask for some data, because we don't need all the details that describes our entities in each synchronization package, because something doesn't change often. So maybe it's appropriate if we have a kind of tracking, a dirty flag on entities that on the client side, so we can ask server to refresh something. We can store, for example, some identifier of a current equipment which is iterated each time it changed. Because at the end we have to handle such situation. So maybe it's a good idea to make a separated server for our chat system, because it's hard to deal with such situation. And going forward, fancy animation here will be. First time was when I thought about how I want to match incoming data model to appropriate place in code which I want to handle a business logic for this data model. The first thought was of course a kind of dictionary, but then I realized that in the result I will search through this dictionary tens of thousands of times per second all the time, and in the result I will almost always retrieve the same handler that is responsible for movement. So I thought about pulling out the most common used handler and put it at the front of this dictionary to avoid this common search. But why should we search at all? It's our network request. It's a simple structure that contains a serialized data model and a meaningful byte that describes what type of data model is stored in this network request. Later on, using my dependency injection framework built at the top of the AutoFAC, I'm injecting each request handler at the very beginning on client and on the server side, and I put it at the same place in the network request handlers array that is the same like this meaningful byte on the network request that this handler is responsible for. So, in other words, when I'm receiving the request with identifier 7, without searching anything, I'm just pushing this request to the 7th index of my request handlers array. When I'm creating a request, I'm taking some kind of data model, I serialize it to the network request with this meaningful byte, and I'm pushing it to the appropriate outgoing request queue that will be sent through the other thread. And when I'm sending this request from the queue, I serialize them as outgoing as network request array. In this moment, I'm clearing this queue after I serialize it, but it's not appropriate for each type of game because, like in Overwatch, for example, you can need a kind of command buffer in some games, so you may have more than one outgoing request queue on unreliable socket, which will be cleared on demand of the server. So you can iterate some kind of number on the requests, and each request with a positive number can be treated on the server side like a request from the command buffer, and the server can track what request was already handled from this particular client, and then server can tell about it to the client, and then client can remove such requests from the command buffer. So this clear is optional. So if I know how I serialize outgoing requests, I also know how to treat incoming requests from the stream, because I always can deserialize it like a network request array. And then without searching anything, I'm just pushing this request to the appropriate handler through some generic abstraction, so I don't have to search for any particular type of logic here. So this approach I named index-oriented data. I applied in the whole backend that have to perform through huge amount of data. Because if we think about what server is doing in most of the time, if we skip the gameplay layer, of course, because we're not talking about this today, we can imagine that server just goes through all the entities, receive, deserialize, and handle incoming requests, and pushing outgoing requests that probably mostly come from the other threads. Our network entity is described by a simple structure that contains a network identifier that comes from the database, or is assigned from the server to make the particular entity unique between all the clients. An internal identifier that is different on each client, on the server, and this internal identifier represents memory layout for this entity. So it's just an index that represents this entity in each structure that this entity is associated with. So to make it possible, at the very beginning I have to adapt the server limit. I'm injecting the network settings to each type of module that need to prepare appropriate structures. And for example, when a server is starting, I already have 2,000 of outgoing request queues for 1,000 clients, even if there is no even one client connected, because I want to avoid memory fragmentation. So when I'm proceeding through the clients, in this example on the UDP thread, I'm always in the context of the client. I'm touching his index. And this index is the same like his internal identifier. And in result, when I'm proceeding through the clients and I'm in the context of client with identifier, internal identifier free, I can be sure that any type of structure that I inject to my system, I can retrieve, write, or whatever I need, only the data that is associated with this entity without searching for it. So when I'm proceeding through all of this, everything is already in cached because of CPU prediction. Also, I can vectorize through the structures, and there will be, I can set a couple of threads that can iterate like on the buckets, and there is no race conditions between them. Okay, going forward, it's obvious knowledge, but it's something that have to be said. You have to use reliable and unreliable communication. Reliable, I mean a TCP, of course, which you have to treat like a heavier and crippled by additional logic, which is to ensure that your packages has arrived and arrived in appropriate order. And you use reliable communication for each action that have a single character, like reloading a weapon, clicking UI button, establishing connection. But most of our network traffic is filled up by unreliable datagrams. We can be sure that all of these packages will be received by a receiver, but probably we don't care if we send a lot of them. And we can replace, in some games, we can replace this TCP reliable communication by a command buffer. There is no big differences between TCP and UDP until we lost packages, and when we are in the internet, we will lose the packages. Then problem may occur with the TCP, because if we don't receive ACK flag at the time, we're sending the same request again on TCP, and it can lead us to some problems. Our TCP connection with the client can stuck forever even. Then we have to create a second one behind the scene that will replace this first one. So sometimes it's good choice to remove the TCP connection at all. It's great for establishing this handshake with the server. Because in the case of C# and in the case of server, the first object that we are starting from is a TCP listener. It's an object that helps us, that let us bind incoming network stream from the internet with our host machine and host application. So we need a public forwarded port to our machine. Then we can create a TCP client from accepted connection. Because on the other hand, we have a client. This client uses a TCP client to establish connection with the server. So we have to provide to him an address and public forwarded port to our host machine. So by calling a get stream, we can initiate a handshake with the server. And we have to remember that we need to disable Nagel algorithm, which is not appropriate for games. So in this moment, we have a TCP client and, on both sides, and we can communicate with them. But in this moment, server knew barely nothing about the client, so I added some kind of unconfirmed clients sub-layer in the network layer that doesn't use queues. In order to keep it clear and simple, this layer just sending up to 2 requests to the client and receive only 1 request from the client. So what I'm doing, I'm serialize a confirmation request as a network request array, and I push it directly through the socket to the client. So client may receive this request and push some authorization token to the server that was retrieved earlier from the web service. Server doesn't need this private key to decrypt this authorization token because it's pointless. What server is doing, server on this unconfirmed sublier, which can be asynchronous, work asynchronously, push this authorization token again to the web service, and then if web service validated and everything goes well, what I'm doing, I'm taking the UDP port from the UDP pool, and I'm taking the endpoint that I already know from the TCP connection. I'm assign the new port to this endpoint, and I establish a new UDP client with this client. Then I'm sending to him this new UDP port through the established TCP connection, and in result, at the end, client may establish a new connection, new TCP connection, TCP client with the server. And so now we have a TCP and UDP clients on both sides. But here is a useful tip that can send you a lot of debugging. You have to send the first datagram from the client to the server, because until it happened, server doesn't know the real endpoint on UDP client that is assigned to the client. Because when he received the first request, this endpoint will be refreshed, and then we can communicate in both sides. So everything is established. And in a case of UDP, it's simple. We just send a byte array and its length, nothing fancy. In a case of TCP, there are two main approaches, but we'll talk about this one from the slide. We have predefined prefix length, which is often just integer const with value of 4, because TCP packet can be split into the parts, into some smaller portions in the wire. So before we send the request on TCP, what we have to do, we have to convert this request to the 4th byte array that contains a length of this request, of its following request. So we always send, at first we send the 4th byte arrays, and then we send following requests just after that. So when we are receiving this request, the first what we have to do is we have to read this 4-byte array from incoming stream. We can read a length from this 4-byte array, and then we can be sure that for how long we have to read from incoming stream until we receive the whole request. So we can be sure that when we try to deserialize it into some kind of type that we want, we can be sure that it's the whole request here. And okay, for C# programmers, be aware of using async programming in your network code if you want to scale your game, because it hides real performance from the programmer. If we imagine that we have our receiving loop and we have 100 clients connected, so we are, by calling begin receive, what is happening, we are creating a small task that will be handled later by thread pool. So we are pushing for TCP and UDP connection, we are pushing 200 of the small tasks to the thread pool per frame. And these tasks cost barely nothing in a CPU time, in opposite to switching between thread contexts. So it's much cheaper if we have a persistent thread that sends our requests without asynchronously code. And all of this can be easily found on Stack Overflow, so there is nothing fancy here. What is worth to mention is that the UDP approach, which you have a separated socket with each client, because you don't have a public UDP client that reads all the streams that comes from all the clients, because it's not safe. And that's pretty all in this topic. So be aware of that. And going forward, what is the difference between shooters and MMORPGs? Why shooters have tens of players and MMORPGs have thousands of them? So everything is about computational complexity of synchronization, which is quite high in shooters, and it have to be. Because if we play at Daisy, for example, and we climb above the hill, or we take a helicopter, then we can see even a source of light that is miles away from us, because server have to send almost everything to us all the time, because that's how this gameplay works. But in isometric MMORPG, it's a great example for using chunks. You can think about a chunk like a two-dimensional square or three-dimensional cube in games like Minecraft or Star Citizen, which can very cheap and fast translate your entity position into something more appropriate X and Y coordinates. So you can very fast and easy figure it out what entity is around the another. So in the result, you can prepare a situation in which you serialized only a circle of interest that's happening inside a particular chunk or the neighboring chunk to the given entity that is associated with this chunk. It's a gameplay part, but it's necessary in this lecture. So in Unity, I'm making it through the job system. What I'm doing, I'm iterating through all the entities. I'm checking if the current position translated to the chunk is different than current chunk assigned to this entity. And if it is different, it means that in this frame, this entity cross a border of the current chunk. So what I'm doing, I'm put a dirty flag on such entity. And there is another job system that proceed only the dirty entities and reassign them from the old chunk to the new one. Chunks exist only on the server side, so I'm calculating them at the very beginning. In this example, I store all the neighbors, but it's not a good choice. If you can keep your players away from the borders of the map, it's much more appropriate if you just calculate it at runtime, because it's just a 2-integer offset. So it costs a lot to store all of these neighbors and all of these chunks. The main source of our outgoing request queue in such outgoing request to the queues in such game comes from the chunk manager, or however you name it. What I'm doing, I'm iterate through all the chunks. I'm checking if there is any client in this particular chunk or the neighboring chunk, and if there is anyone around, then I grab all the data that describes all the entities inside this chunk. I'm creating a single request from that, and I push it to the outgoing request to each client that is around. So it's the last place which we can remove some non-appropriate data from this request, because someone can be invisible, or we don't want to send the data that describes one entity to another, because maybe, for example, because of some other gameplay validation, like raycasting, because when we push it, it's in the network layer, so network layer shouldn't be responsible for validate our data. So looking at this architecture, the first what we have is unconfirmed clients sublayer, which can work asynchronously, and it's good to have such separation, because all the problems that may occur during establishing new connections and calling the web service that have to communicate with the database happening in this layer. So it doesn't corrupt our main synchronization loop, which we have here. We can have, for example, listening and sending thread. It should be natural choice, but in practice, it's not a good choice, because much more appropriate is to have TCP and UDP thread. Or in a smaller project, we can combine them together. But if we have a listening thread and sending thread, both of these threads using the same TCP, for example, TCP client to receive and send the request, so we need logs above them. In this type of architecture, there is always only one thread that touch the particular TCP client or UDP client. Of course, we can have more threads in such sublayer, so we can for example, split our clients to buckets and run two UDP threads that handle our, for example, serialization, all that stuff. And at the end, we have chunk manager, and that it's the main source of our outgoing requests. So what we need is a log above each outgoing request queue, because the queues may come from many threads, and we cannot be sure when someone wants to push a new request. So it may happen in the same time when we try to serialize it and push it through the socket. And at the end, I wanted to show you the most appropriate way of handling data models, because, as you can see, it's an example of a network request handler. So it's registered, and I push some type of data model to it. So everything what's happening here, there is no logic here. I'm just deserialize some type of data model, and I push it to the appropriate structure, to the appropriate index that this entity is associated with. So as I said, I'm always in the context of some entity. So when I receive a request from the stream, I always know who is related to this data that I just deserialize. So as you can see, nothing happening here. I have a middleware in a form of structure that is a bridge between a network layer and gameplay layer. And we can have in our gameplay layer, we can have a component systems or job systems that proceed, that do something with this data, but we don't care from our network layer. So I was asked to cut some slides from presentation, so I done it. It's some benchmarks that I prepared for a current game. We can easily measure a kind of bandwidth of our server. So even if the network, in the local network, you can just connect clients through the Wi-Fi, so through the Wi-Fi. So you can push a huge amount of data to your server. You can measure how much of that you can receive, how much you can send from your server. So I can handle much more than this 30,000 requests, but it depends on the project. For some games, we can handle tens of thousands of clients probably, but it depends. And I measured that for a mobile communication with Azure Virtual Machine, the RTT was something around 20 milliseconds. So that's pretty all. I don't know how it takes. Okay. Thank you.
And the questions?
Hi, thank you for the talk. I'm trying to understand one thing, how this solution would work in practice, because you mentioned that most of the calculations of the gameplay does happen on the server side, not on the client side. Mm-hmm. So I imagine a situation where, for example, a player wants to move, right? So, mm-hmm. for example, either keeps their gamepad to the right, for example, or clicks somewhere, right? Mm-hmm. So the engine has to render frame by frame, 60 frames per second, right? If someone is moving. Mm-hmm. But if the server is doing the calculations, would it actually send every frame the data? It doesn't seem doable with 20 millisecond round trip, right? So how does it happen? Like frame by frame, how does the client know if it should move or not move the client, or does it approximate? So that's my question.
So it's more about the design of the game, but it's you can perform a kind of client-side movement to make your game more responsive. But as I said, if your position will be diffused with the one from the server, then you have not appropriate data that have nothing common with the reality. So there are a couple of tricks that you you can implement. So your client may be more responsive. So you just push a button and your client start to move, but in parallel you're sending the request to the server, and these intentions should be treated like somehow. You can synchronize the frames between your client and the server, so you can validate what's happening in a particular frame, because it's a great talk about that related to Overwatch from some GDC. I don't remember the year of this GDC, but as I mentioned at the beginning, it's more about your client, not the server, because it's more about the design, how you want to handle this latency, these packages lost. So you have to figure it out what will be best for your situation, for your game, how you want to move maybe a little faster at the very beginning when direction change on the server side. Maybe you need some speed up to pay on the server side for this latency. It depends on the game.
Okay. Anyone?
Here?
Okay.
Well, I have a question. It's regarding multiple server architecture. I don't know if you have experience in that. I'm having problem with this, with race conditions between multiple servers. So each of the server has its own world truth, and this truth must be synchronized. And let's say that 3 servers are sending to themselves a mutually exclusive action. Let's say 3 players connected to 3 different servers are trying to grab a single item. So I never found an elegant way to solve that kind of synchronization or race conditions between servers.
I thought about it once, but I figured out that it will be more appropriate if I stick with the single server architecture, in order that I'm working on that for 2 years alone. For now, I'm using it in a commercial project, but it's hard to test a multi-server architecture at home. But then I thought about a kind of chunk system, which but yes, I thought about duplication in some you need a border between chunks. So if you split your server, for example, in a x axis, and your client moving around the world just cross the border of the server like a border of the chunk, then you need some kind of place which in the player exists on both servers. So I don't remember how I wanted to deal with that, but I thought about that one server should always have authorization over the other one.
Yes, that's how I implemented it also.
But I never done this. I never work with the multi-server architecture, so it's just what I'm thinking about right now. So.
Okay. Anyone? No? Okay, thank you very much.